Hello, my name is Mark Berkman. I work with Ozen Engineering, and today I have an interesting video. I'm going to be talking about the newer version of Icepak, AEDT Icepak. This is an Ansys tool for thermal analysis. In this tutorial, what we're going to do is to consider an cold plate problem. This problem is going to have both external natural convection and an internal forced convection. We're going to have this water-cooled plate, and we're going to build this model from scratch using AEDT Icepak. So for this purpose, I'm going to hit New in Ansys Electronics Desktop. I'm going to go ahead, click Icepak, and hit OK. So this is going to bring up the setup for an Icepak model. Typically, users would generate their geometry in a separate CAD model and then import it into AEDT Icepak. I'm going to take a different path. I'd like to show you, how to build a simple geometry from scratch using AEDT Icepak capabilities. So I'm going to start by inserting a block. So I go click the draw box button, and then as you can see, it's going to open up this window. And here first I'm going to start defining my cold plate. And my box is going to start at 50 millimeters by 80 millimeter by 70 millimeter position. So these are all in millimeters. I always suggest users to be very careful with units, be consistent always. So our X size is going to be 300. Y size is going to be 140, and the Z size it's going to be 60 millimeters. So once I hit OK, we're going to see our box that is created. So this is our cold plate. Now I'm going to add some cylindrical pipes. So I'm going to hit draw a cylinder, and this is going to have a center point of 100 by 0 by 100. This is going to lie in the y-axis. Our radius will be 90 millimeters. Oh, sorry. Our radius will be 15 millimeters. Our height is going to be 90 millimeters. And once I hit OK, you can see that it kind of protrudes out of our solid domain. Right, I'm gonna add a second one. Again, I'm gonna click cylinder, and this one's going to be shifted further down in the X coordinate. Then its radius again will be 15 millimeters and with the same height of 90. So now we have our solid domain defined. Next step, what I would like to do is I want to take this box, mark box cylinder 1, cylinder 2 using the control button, and here you can see the unite objects. I'm going to go ahead, click this, and these become a single box. So now that I have my cold plate, what I'm going to do is first let me rename it. So I'm going to go to properties. Instead of box 1, I'm going to type in cold plate and hit OK. So you can rename like this. And I would also like to hide this from view. So right click and view, and then hide in active view. Next step is to add our water air solid that essentially will be carved out of our cold plate. So again, let's create a new box or a prism, and we're gonna start this at 60 millimeter, 90 millimeter, 80, and it's going to have slightly smaller dimensions than our cold plate. So let's hit OK. It's going to look like this. And if we look at our cold plate, you can see that it's slightly larger. Now we want to add up our inlets and outlet ports. So I'm going to go ahead and add a cylinder to our system. And the center point is going to be 100, 0, 100. And its radius is going to be 10 millimeters with a height of 90 millimeters. Let's hit OK. And let's add a second one. Now this is going to be shifted again in the X position with the same radius and height. Let's hit OK. Alright, so now we have our box 1, cylinder 3, and cylinder 4, and I would like to merge them into a single object. So I'm going to use the unite object function and hit this. So let's also rename box 1. So let's do properties. And then let's change this to water. Okay, and while we changed it, what we can also do is maybe change the material itself to water. So we can go here and we can hit edit, and under here this pops up a new window which has a big material database. So I'll type water here. I'm just gonna pick water at about room temperature, and I'm gonna hit OK. So let's hit apply, and now we have water defined as a new material, as a fluid. So essentially at this point we have our air region, which is our enclosure. It encloses our cold plate, and then we have our water stream, our coolant running inside the cold plate. The next step involves some heat source, and we can define this heat source of multiple different ways. We can add another prism type 3D object and use it as a heat source. But here what I would like to do is use a tin plate. So I'm gonna go ahead and I'm gonna add a rectangular object or a plate. So I'm gonna go ahead, click this, and now what we want to do is again define its position. So our first plate would be at this location. And this one now is going to lie in the Z plane. And let's see, its length is going to be 260 millimeters, and let's put a width of 100. Let's hit OK. So it looks like I mixed up the length and the width. The way to fix it is we go back to create rectangle. We can see the properties, so we need to swap these two numbers. And then hit apply, hit OK, and let's see. Okay, so our rectangle seems to be positioned a little away, so it looks like I do not have the correct z coordinate. So what I need to do is change this number. That's 60. Probably looks like maybe it needs to be 70. Nope. So should have been 80. And this is, how we can adjust. And now we can see our plate. Okay, so let's add our second plate. And then this one's gonna be on the other side of our cooling system. And again, this will be at 100, 130 to be in the z-axis with a width of, let's see, let's again try 100, 260. Let's see now if I can orient it right. So again, looks like I need to do some shifting. Go back here, swap these values. Hit OK. Let's see. Looks like our Z location is not correct. Let's make this 120. Okay, so now it's correctly placed on the face. This step essentially completed our geometric setup. Now what we want to do is assign boundary conditions, thermal conditions, etc. So I'm going to go to my rectangle 1. I'm going to do a right click, and then I'm going to do assign thermal and select the plate option. This is going to be a conducting plate and act as a heat source. So let's say this is a 10 millimeter plate which has a total power generation of 200 watts. And again, let's go to our backside, same operation, plate conducting, 10 millimeters with 200 watts. In the next step, I'm going to readjust our enclosure size so that it's doing the right things. What I'd like to do is take the face, the Y minimum face, and align it with the inlet of these pipes, and also maybe take the X coordinate, X min and X max, a little farther from the object because we're going to have natural convection in the X direction. So for this purpose, I can go click create region, and what I can do is play with these options. So here what I'm going to do is I'm going to consider the Y minimum, so Y minus, and I really actually want to have a 0% offset. So if I hit enter, it's going to align correctly. Then maybe in the X direction, I want to go to 75% and 75% in both directions, and give some more space in that direction. Okay, so that's great. And now what I would like to do is I would like to go to my water and hit the F button to select the face right here, and as you can see only this face is selected. And I want to assign this surface as a mass flow inlet. So how do I do that? I go click right button, I'm going to do assign thermal. It's going to be an opening. Inlets and outlets are called openings, and then we're going to pick pick opening. So I'll just call this water inlet, and we want the temperature to be ambient. I want to define a velocity. This velocity will be in the positive y direction, so I'm going to put in 0.2 meters per second of velocity and hit OK. So now what you can see is under thermal, you can see the objects that I've defined. We've defined 2 conducting plates. We also defined the water inlet. So next step, let's pick our outlet face, and again similar operation, assign thermal opening free, and this time we're just going to assign it to ambient pressure. So it's going to be water outlet, and let's hit OK. What we're going to do is whatever wall we do not, or boundary we do not define, it's going to be turned into an adiabatic wall. In this particular case, we're going to have some natural convection flow, and gravity is in the negative x direction. So what we want to do is go to our air region, pick this face, and then if we do control, pick this other face, and again I want to assign these faces to opening, and they're going to be free, and then we're not they're just pressure type boundary conditions, so it's going to freely allow the flow to go in and out based on buoyancy. And I hit OK. So now we have, and the rest of the enclosure, it's going to be assumed as walls. Since our geometry and boundary conditions are set up, the next step is going to be meshing. So I'd like to go back to Icepak, click on the simulation button, and then I'm going to go click global mesh settings. So here, what I'm going to do is I'm just going to use the simplest meshing option because our geometry is pretty simple. Just going to leave it as, baseline settings, and I'm just going to hit OK. Next step, we're going to generate the mesh. So let's click on it. And what now it wants to do is save this project. So you can give any name here. I'm just going to hit save and move on. So now project is being saved, and then meshing is underway. So you can kind of see the progress in the progress window on the bottom right hand side. And what actually happened is it already generated the mesh. It's a fairly small domain with simple configuration, so it only has about 30,000 elements, and which is good enough for this problem. What we want to do is typically, let's go first check our quality. So face alignment, it's much higher than about 5%. Skewness, it's much higher than 2%. So it looks like the quality is very well. But what I'd like to still do is kind of visually check the mesh, right? We want a bit of a finer mesh around our features. So we're we already have a cut plane that's showing the mesh. I'm gonna go ahead, mark the objects and hide them. So I go right click, view, hide selection. Now we can see the mesh. So it's a fairly coarse mesh. A finer mesh could be generated, which would most likely give slightly better results, but because this is a demonstration, we can live with this mesh. Another thing I'd like to comment is if you use this automatic meshing method, it's going to do a multi-level meshing or a cut cell meshing approach. And as you can see, it starts with the coarsest mesh on the outside, and then as it approaches to the features, it starts dividing the cells by 2. And that's how it does it. Next step in our process is to set up the case, the final boundary conditions, operating conditions, and then numerical conditions, etc. So for this purpose, I'm gonna go under Icepak. I'm gonna select design settings, and this is kind of hidden in a place which I don't like, but it is where it is right now. So here you have control over some operating conditions. So ambient conditions, temperature and radiation temperature is set at 20 degrees Celsius, and then your gauge pressure is 0. When you have a natural convection type problem, you want to definitely define your gravity vector in the right direction. So in our particular case, it's in the x direction, it's in the negative x direction. And validations, export settings, mesh, advanced, we really don't need to go there. If we want to include altitude effects, if this is operating somehow on an aircraft or something, you can include an altitude here. But important things a lot of times we want to use is define your ambient conditions, temperature, pressure, and if you care about buoyancy, you want to define your gravity, and then you hit OK. So another key is under simulation, we want to hit the setup button, and this is going to define the physics of our problem as well as the numerics. So typically, I want to do up to about 300 iterations. We're going to be solving for temperature and flow. We're going to let's turn on turbulence, and then we have many turbulence models to pick from. For this particular case, I'll just stick with the zero equation model. Better types of models are typically realizable 2-equation or K omega SSD type models further down the list. So if you want to capture more details of the boundary layer, etc., you may want to put a finer mesh in those regions as well as use those turbulence models. Let's turn on our radiation model. We're going to use discrete ordinates, and we talked about this a couple of times. We're going to include gravity for our problem. So let's check that on, and let's look at our convergence. So I'm going to leave the convergence criteria as it is. This is good for our problem. If you want tighter convergence, you typically suggestion would be to increase the energy. Drop the energy residuals to maybe 1e to minus 9 or even 12. But in our case, we'll stick with this. Solver settings, because we do have natural convection, we want to start out with a really small value, and we're going to do in the positive x direction opposite to the gravity direction. We can also check advanced options. We're not going to go change anything here, but if you have convergence issues, then you may want to come here and maybe play with the under relaxation factors, or use some stabilization techniques. Let's look at our radiation. Typically, we can do 5 flow iterations per radiation, because radiation is expensive to solve. And if you have the discretization at 1, this is the coarsest level, you should go as high as 3 for all of these. Don't go beyond. It may get very expensive to solve. So I'm going to stay with this coarse level. And, if you can save your defaults so that, you can use them in the future. But, so I'm going to hit OK. So this is, we essentially done our problem setup as well. Since we want to get a converged solution, what we want to do is monitor some key values at each iteration, so that we can check the convergence. What you want out of convergence is that the monitored values should stop changing with iterations. Because this is a thermal problem, we want to track temperatures. We also have some fluid flow. So we're going to add one monitor to maybe track the water mass flow rate. So how can we do this? So let's, take our, for example, water inlet, or could be outlet. Let's pick our face. And then if we do a right click, we can assign a monitor on this face. And what we want to do is we want to look at the mass flow. So we hit OK. And as you'll notice, it's going to add another object under monitor. And if we like, we can change these names. But we don't need to at this time. So let's also look at our conducting plate. So let's look at, our first one. So let's assign on this face. Probably it's better to track maximum temperature here. And then I'm going to go to my rectangle 2. Then assign monitor on the face, and again temperature maximum. Hit OK. So now we can kind of review our monitor locations, and we're all ready to run. So at this point, what we want to do is maybe hit the validate button, see if there are any errors. Looks like our setup is correct, and we can close this window. Next step is we can hit analyze all, and because this is such a small model, it's going to run fairly quickly. So let me click this button, and we're going to see some progress in the right hand side corner. What it's doing right now is preparing an input model for Fluent. As you know, in the background, Ansys Fluent CFD solver is being used. And once the run is complete, Fluent is going to write out the results, and then it's going to be imported back into Icepak. And if there are any problems, we're going to see some messages here, with some bad news. But what we're seeing is, it's going through iterations. You can kind of see it's around 110 iteration there. If it doesn't meet the convergence criteria within 300, it's going to run all the way up to 300 iterations and then write the results. And, looks like it's going to go all the way to the 300 limit. So now, now you can see the progress, and looks like we have a successful solution. So we made it to our final step of our project. We, started from scratch, built up our cold plate model, assigned operating and boundary conditions. We defined our solution setup, monitors, etc. We executed the model. So next step is post-processing, which is actually a critical step where you get to look at the solutions. You want to make sure the results do make sense, because there are lots of sources of error, such as maybe meshing quality, picking wrong models, inputting, wrong numbers, etc. So before presenting these results to your boss or your customer, what you would like to do is make sure the results are correct. One thing, obviously I'd like to do is, I go under Icepak, I click results. First thing typically you want to look at is the solution data. So once you click this, it is going to bring up a window, and it's going to have this summary about the solver running, etc. But more interesting stuff is in the second tab, which is the residual. So this is essentially what's happening. These are tracking the error or the change in the solution for different solution parameters, such as conservation of mass, which I believe is the red one. Yes. So if we uncheck it, we can see it. Then X, Y, Z velocity, I believe, are these three curves. And then we solved for energy, which has the best convergence roughly. And we also had radiation, and as you can see, radiation converged a little later than others. But toward the end, mass did not converge fully. It came close, but did not meet the 3 orders of magnitude. And this is not a problem in this particular case, as we're going to see. We're going to look at our flow monitor. The mass flow rate for water is fixed, so that's good. We're going to look at the thermal results, and if we look at one of them, we start as high, and then it really converged, and the temperature also flattened out. So you can turn this off, see the other one, and it has the same temperature, which does make sense because we kind of have a symmetric geometry with symmetric thermal loads. So it's all good news on this front, and this is the first thing you want to check after getting a solution. Okay, now a lot of times we like to look at vectors or contours to understand the thermal flow. So what I'm going to do is I'm going to go to Icepak, and I'm going to use a toolkit. Under the toolkit, we have different options. So here there are different macros or scripts that are available to users, which help with building geometry, building packages, ECs, etc., or doing different setups, different tools like aligning objects, etc. And then under reporting or post-processing, we see the cut plane. This is a tool I like. So when I click on this is going to bring up a new window. And this window looks a lot like the classic Icepak plane cut function, which a lot of users are used to, and therefore this toolkit was created for users. So right now what it's doing is at an X plane through the center, which you can see here, we can look at contours or vectors. So what I'm going to do is I'm going to check contours, and if I hit create, it's going to show on this plane the temperature variation on this plane. And I can manipulate this plane. So this can also be cut through a Y plane. And if I do create, so now it's going to look like this. So what we kind of see here is the impact of natural convection on the outer side. See, we have the ambient air, colder air, and due to the heat source, as it floats up around the hot objects, it picks up some heat and it gets heated, right? And that's typical with natural convection, you can see. And then inside the domain, we do actually have the water cooling. And again, as the water enters on the inlet side, the water's colder, but then it also heats up a little due to the heat source. All right. Another option might be, on this plane, we can look at the flow vectors. So I'm going to hit create, and it's going to go ahead and essentially, get the flow velocity. And as you can see, we have a fairly slow flow for water, but because we do have a small mass flow rate. And again, about 0.25 meters per second flow, as that's the highest that we're seeing. And that's driven by the buoyancy. Another typical post-processing is, for example, looking at a temperature on a surface. So I'm going to go to my cold plate. I'm going to pick that top surface. And what I can do is I can go to plot fields. I'm going to pick temperature. I'm going to say surface temperature. And let's hit done. So what this is going to do is add the temperature plot on our cold plate. So you can post-process your results multiple different ways, but I try to give a couple of basic examples, and this actually concludes our demonstration for the day. Thank you for your interest.